Hey there, my name is Kevin G. I'm an Algebra 1 and Geometry teacher at Oakland Technical High School. Going to try to make this quick. I'm basically showing you guys how I use draggable points that I've created as digital manipulatives to help students better access some tricky problems in geometry. Quick context, you probably started reading through this question. It is basically pulled from the Exeter math set, which I'll show you guys. It's a set of problems that Exeter has released that are very problem-based. Rather, they're all problem-based. It's a entirely problem-based curriculum. Very cool, very discovery-focused. There's no notes really, but students are discovering concepts as they go through problems. There's ways that they introduce certain things in a really cool way. I really like them a lot, but also can be a little nightmarish for students. You can see they're really text-heavy. Wording can be confusing at times. Really cool math going on, but sometimes not the most accessible stuff. Ergo this. Basically, really simple graph. I've kind of just drawn the line as a student might start the problem, but also given this, but also plotted this draggable point. So this is kind of the digital manipulative component of this. The problem basically asks about Kirby's location after certain time intervals or when Kirby crosses certain things. As you can go, you kind of see the H value is time in this case. I'm at 1 hour, I'm at 2 hours, 1.5 hours, etc. So it can help a student access this problem where before they might just be seeing like, okay, I have this line, like what am I actually doing now? And this has just been a way that I've kind of ad hoc just been doing this when we're going over these throughout the week. I give them on Friday to be due the next Friday. I'll often just show kind of a graph like this or try to animate something to bring the problem to life for students. My biggest thing that I want to use though is how to share these with students also. I'm curious what y'all think. This is kind of also a puzzle I'm throwing back at you guys, but right now I'm starting to think I should save these as calculators. I have each of these graphs saved for certain problems that are trickier. I can share these with students on my website or via Google Classroom, whatever really, to give them as kind of additional hints that they can use either on their own at home or that I could share out in class for a day if we start them in class together. Just depends on the week. This is a second problem. Basically, a line that you graph, they give you the equation, and then there's this triangle that's created with the two axes, and you want to inscribe a square in this and figure out how large that square is. Really cool problem. There ends up being a 3, 4, 5 right triangle created by this line. This one's not as natural as the other one. It's not a parametric question, so this point is kind of just something that is basically a draggable vertex for this square. Turns it into an estimation problem really quickly. Like this problem involves some abstraction. You kind of have to think algebraically to find those missing side lengths, try to set up an algebraic expression, write a proportion to solve. I think is a way a lot of students will try to do it, but a lot of the place where students might get stuck. This really quickly makes the problem kind of like, oh, like I can see this, where might my X and my Y value be equal, and give a student a place to start that problem instead. Last one really quick. This one's a bit more of a stretch, but here's kind of a cool way to look at one of my favorite Exeter problems we've done. It's the 64 equals 65 area paradox. There's these 4 shapes that are put together to form a 64 square unit square versus a 65 square unit rectangle. And it's like, figure out what happens. A lot of students started graphing these in class. So they got grid paper, started drawing these. I figured, why don't we use Desmos to do this? You can see this. And immediately you can kind of see like, oh, this sliver right here might be that hidden area that comes into play, which it is. Key to understanding this problem really comes into slopes. So again, digital manipulative, I have this point. As you start to drag this along the blue line, especially if you keep going, you can kind of see, all right, I color coded these lines, but you can see what happens to this point as you continue. What's the path that it follows is just like could be a great conversation point for students while we're going over this problem, but also a possible hint as they're going through it about how to think through a really high quality written explanation for this. So yeah, thanks for y'all's time. This is just me using some basic Desmos features to try and answer the bigger picture question of how do I make some of these really great math puzzles that are a bit wordy and complex more accessible and visual to students. Thanks so much.